Okay, we are now recording. You can see me okay? Everybody see me okay? All right, okay. So I've got this set up so that when I start lecturing, you're gonna see, I'm gonna share a screen with you that has all my notes on it and some blanks for where we work stuff together. So it'll look kind of like a lecture. I wanna talk to you a little bit first about the assignment sheet. And I'm going to share the screen with you and show you what you're going to be seeing. So hang on one second, and then I'll ask you what you're looking at here. All right, come on. There you go. All right, can you guys see the document that I've got up here?
Yeah.
Can everybody see it? It says Math 210 online, and it's a syllabus kind of thing. Now, sometimes we will get feedback, and if we get a lot of feedback, I'm going to have to get you to turn your mics off, and then you can turn them on as you want me to ask questions, okay? As you want to ask questions. But, okay, here's Tiara coming up. Okay, good. Hang on a second. Let's get her.
You hear my TV? Should I turn it off?
Say that again? No, I can't hear. I can't hear the TV, I don't think. So anyway. So let me talk to you about the syllabus. This is kind of a rewrite of what we started before break. I had started into chapter 4, and that first section of chapter 4 is really long, and I had done one section of it already, and that was 2 weeks ago, and it seems like 2 years ago. All right, so I'm going to start by doing a little bit of a review of that, and that will actually be your first assignment due will be on the review stuff that I do today. And if you look down here in a blocked thing, I have when the assignments are due. You're going to email it to me or scan it and mail it to me. I've got folders set up so that all your stuff that you send me goes into a folder, and I know where it is. So the first one is on this few problems that we'll have, and I'd already assigned some of this. I don't know how many people looked at it, but once I do the review, you might want to start looking at this. I put it due on Thursday. I'm having some of the due dates that are not on class dates. That's because I felt like it was rushing it and not giving you a chance to ask a question on the next time. So pay a careful attention to the due dates and get it into me pretty quickly. I did want to say a little bit about midterm grades. Your midterm grades will be just based on what we had. They're due, as far as the faculty is concerned, on Wednesday. I will turn your midterm grade in according to whatever it was after that second test. That's one reason I went ahead and got it graded and got it back to you. As you know, I think probably from emails that you've gotten from the school, that we're going to a grading system that's pass no credit. That's a lot more complicated than it sounds. You can opt to take a grade, a regular grade. Now, our no credit starts below C-. So for instance, if for some reason you got a D and you wanted your D instead of a no credit would mean you'd have to take the course all over again. A D would mean you've taken the course in bad times. But we need to have personal conversations about this. So as it goes further, and as I understand more about what the policy is going to be for the school. But the default setting for your grade now is pass no credit. Questions, anybody? Everybody okay with that? Okay. So let's see, what else did I want to tell you? I will check the roll. I've checked to see who's here every day, but if you can't make it for some reason, all of these are going to be recorded, and they're going to be uploaded to a YouTube video, and that YouTube video link is going to be in Moodle for that day. Okay, so it's got two benefits. If you miss class, you can see it. You can watch it over and over and over again if you can stand to do that. Okay, so if there's something you didn't understand, you want to hear me say it again, you can go back, look at it. It could be helpful. I'm going to establish some office hours eventually. Everything's sort of up in the air. I want to meet with every class now before I make a decision about when my office hours will be, whether they'll be by appointment or whatever. I just want to make sure everybody could get online. And I think I've got just about everybody now. So I'm looking at my thumbnails. I'm not seeing everybody. Let me expand it and see what happens. Still don't have everybody. Okay, all right, I don't have quite everybody, but if anybody just speak up if you've got a question. If I can't see you, I'll just identify yourself and I'll answer your question. Let's just go ahead and start. Let me show you what I've got here. This setup that I've got, I will tell you that I was a little panicked about this, to say the very least, as probably everybody else has been. I went almost immediately to a former student of mine who's an award-winning teacher online, and I said, Chris, you gotta help me. So she was good about that, and she set me up with some good stuff that without her help I couldn't have done. So a lot of times students eventually learn more than the professor. So there you go. Okay, so what I get to do on this document is go back to a listing of my topics that I've planned out. Okay, so can everybody see that? Is everybody okay with that? It's got what I was working on a minute ago was the assignment sheet 1. What I'm going to do right now is click on this section 4.1.1, which will be the little bit of review on this IVP and BVP. IVP, remember, was initial value problem, and BVP was boundary value problem. Okay, so I'm gonna click on that, and actually I keep clicking on the wrong things here. I have to tap it on my iPad that's hooked up here, so if I keep clicking on the computer, it won't do a darn thing. But if I do that, it'll come back to my notes. All right. So what I want to do is just review this stuff that we started chapter 4 with. And this section is so long because it lays the foundation for everything we're going to do in chapter 4. And it's a lot of theory and it's a lot of definitions. But once we get that under our belts, some of these techniques for solving these things will seem a lot easier, right? So what we started with was linear nth order DEs. And remember, just to be linear, we don't have powers on these derivatives, right? We may have a function of x here, and all the coefficients are functions of x. We have dealt with this specifically when we did first order. We know how to solve first order. We do not know how to solve anything of an order higher than that right now. But what we had, in addition to the nth order DE, was we had these conditions. And you guys have worked with conditions too when we had, we were trying to find the C that makes this work for these conditions. In an initial value problem, the conditions are all given at the same point. So for instance, we'll say the value of the function at x naught is y naught, the value of the first derivative at x naught is y1, and so on and so forth. We get these n conditions here up to the next to last derivative there, right? So that's what makes an initial value problem, different from a boundary value problem, which we'll talk about in a minute. Now, let's take a look at, let's take a look at what the first theorem we had was, okay? So the first theorem we had in this section was whether a solution exists to this. This is a lot like that theorem we had back in chapter 1 that said it exists on a certain interval if everything's continuous and so forth. But it's for nth order, for any order. If you look at what it says, it talks about the coefficients. That's what a n of x, a n minus 1, all those g of x, they have to be continuous on an interval. And a n of 0, that was the first one, guys. That was the first one. If you look at the DE right there, that was the coefficient right there. And if you remember what we did to find, when we did first order, we divided by that and we identified that p of x, that integrating factor. So that's sort of where how far we've gone. But you can't have that 0 and all of these, all the coefficients, including g of x, need to be continuous if you're going to be satisfy the conditions of this theorem. Now, here's where I'm saying, guys, to save yourself some writing, just watch what I'm doing. I've tried to number every single one of the theorems and given whatever its name is in the book. So just write that down and leave us blank spots if you want to fill it into your notes. It'll save you some writing, because you know, a lot of times you get caught up in the writing and miss what I'm saying. And now you can hear me an infinite number of times, which may or may not be good, but whatever. Okay. All right. So it says, let all those be continuous on an interval, and let an of x be non-zero. If x naught is any point in this interval, then a solution y of x of the initial value problem exists on the interval and is unique. It exists and is unique. So let me give you a couple of examples. This is what order, guys? And I'll see if I can hear you. What order is that? Anybody can speak up. What order DE is that?
Third.
Third, yeah. It's third order because we got a highest derivative is 3. Notice it's got constant coefficients and it's equal to 0. We're going to equal to 0 now. When I say something's homogeneous, it doesn't have anything to do with the homogeneous that we had on the first test, on this last test. It has to do with the fact that the DE is equal to 0. In other words, the G of x that's on the right side of the equal sign is 0. So what we've got here is a third order linear DE. Look at what the conditions say. The conditions say y of 1 equals 0, y prime of 1 equals 0, y double prime of 1 equals 0. Point is, they're all at the same spot. This is an initial value problem, right? All of the coefficients are continuous, all right? G of x is continuous. That's non-zero. 3 is never going to be 0. So all the conditions are satisfied. Now, here's Haley's favorite part here. I remember we had problems sometimes where we were talking about, can you see a solution to this? Is there an obvious solution to this, guys? Do you see an obvious solution to that?
0.
0. Yeah, there's an obvious solution to it. It's 0. So let me show you what else I can do here, which is kind of nice. The solution is y equals 0. So what I can do on, and I'll leave what I write on these PDFs. This program allows me to write on top of the PDF with whatever color I want. That's kind of nice. So since it'll set it apart. On the recording, it'll all be there. I can erase this in case, if I make a mistake, try to let me know. I'm gonna try not to make any mistakes, but I can just say, oh, wait a minute, that's not right, and it's gone, okay? So I can erase it, I can put it back in, but what we see here is that y equals 0 is an obvious solution, okay? Now, the question then, is it unique? Well, we had all these things satisfied. An of x was not 0. Not all the coefficients were constants. They're all continuous. They're constant continuous functions or continuous constant functions. So do we have, this is the solution that I see. Is it unique? Does it satisfy the conditions? And I see one that's a solution. Is it the only solution? Well, if it satisfies those conditions, it definitely is. Okay, so the answer is yes. All right, because it satisfies all the conditions of those things. So it's unique. Okay. Kaylee.
Conditions have to be continuous.
Yes.
Coefficient cannot equal 0.
The coefficient on the highest order derivative can't be 0. Yeah.
Okay.
So what you see is all of these have to be continuous, and an of x, that first one, can't be 0. I'll show you an example where it isn't in a minute. Okay.
Okay.
All right. So is everybody okay on that? Everybody good? Okay. So so let's go up a little ways. Let's take another example. Notice that this one is a second order linear DE. The coefficients are definitely continuous, so we satisfy that part of the theorem. There's a problem here though, right here. There's that an of x. That an of x there can be 0. Where could it be 0, guys?
At 0.
At 0. At 0. And notice that your conditions include 0. That's a problem. That's a problem. So if I had said, you know, y of 10 equal 3 and y prime of 10 equal 1, then I wouldn't be in that problem area where that thing is 0. So the question is, does it possess a unique solution? Not necessarily. All right, so not necessarily. I'm not guaranteed that anyway. These pens are hard to write with, guys. So this is where I'm use my eraser. And you might want to just write it as I'm saying it because it's sort of hard. Not necessarily. Okay, so actually, if you look at this y equal cx squared plus x plus 3, that can be verified to be a solution. But it's clearly not unique because apparently it looks like C could be what? I mean, C could be anything. And if I test it, if you were to check that in here, if you were to take the second derivative of that thing, you would see that the C drops out, so C could be anything. It is not unique. It's not unique, okay? Because C is arbitrary. No matter what C is, if you plug it into that original equation right there, you're gonna get it answering or being a solution to the DE. So you got to have both of that condition where the AN of X is non-zero. Okay, let me show you another one. The next one, I'm gonna do a little drawing here. The next one is y double prime plus secant x y prime plus 2y equal x. Initial conditions are y of 0 equal 1 and y of 0 equals 0. So I'm safe right here because AN of X is 1. So that's not going to be 0 anywhere. I don't have a problem with that. I do have a bit of a problem with this one. Okay. 2 is not a problem because it's continuous everywhere. That's continuous everywhere. Secant is not continuous everywhere. Okay, secant is not continuous everywhere. What is the secant? What is the secant? In terms of, think trig, what's the secant, guys? What's the definition of secant? How do you remember what secant is? Anybody? Can anybody hear me?
Is it 1 over cosine?
Yeah, secant's 1 over cosine. I'm trying to find everybody in here. Yeah, okay. Let's see. All right, so secant is just 1 over cosine. Okay, so let's just for a minute, let's look at what the secant looks like. Now, I don't know if you've got in your head what secant looks like or not. The nice part of us going online is you can use your calculus book, you can use your DE book. Calculus book should show you things like what the cosine looks like and so forth, or what the secant looks like. But let me show you a way that I like to remember of what the cosine or the secant looks like. I know what the cosine looks like. If I look at 1 and minus 1, I know that the cosine looks like that, and the period is 0 to 2 pi. Okay. Where does it cut the axis right here, guys? Where does it? And some of you are muted. I'm going to unmute. Wait a minute. Let me unmute you and see how things work here. I'm going to unmute Damaris. I'm going to unmute Brittany. I'm going to unmute. I'm getting a little bit of feedback, but I'm going to try. Okay, Tara's okay. Allison's unmuted. Okay. So all the ones I can see, I think I've got them unmuted. Okay. So there's the cosine. So tell me where that cosine is 0. Think around the unit circle for me, guys, and tell me where the cosine is 0. Where's the cosine equal to 0? Where?
Pi halves.
I can't. Who's that talking? I can't hear. I can't quite hear you.
It's Allison.
Oh, Allison.
Pi halves.
Yep. Okay, that's right. Pi over 2, and this other place is 3 pi over 2. Yeah, that's right. Okay. So if you extend the cosine a little bit further this way, there's another place right here at minus pi over 2. Okay, that's minus pi over 2. So that's what cosine looks like. So here's why I'm showing you the cosine. This is the way I remember what secant is doing. I'm showing you the cosine because anywhere the cosine is 0, the secant's going to be undefined. Okay? Secant's going to be undefined. So anywhere the cosine is 0, there's actually going to be an asymptote for the secant. So let's look at that. I'm going to show you, let's see, I'm going to change colors here. Okay, so I'm going to draw an asymptote right there. Okay, and that's where the secant would have its asymptotes. Everybody okay with that? And here's how, and another place, let's do this one. Another place right there, right? It would be at all those odd multiples of pi over 2. And here's how I remember what the secant looks like. I'm going to pick up another color here, guys, and see what I can do. I don't know. Let's see how green works. Because secant is 1 over cosine, what it's going to do is just flip all these values that were in cosine. So for instance, if it were 1, 1 over 1 would be 1. And what I would do is I'd essentially draw that, and the next one might look like something like down there. So that's what the secant looks like. Now, let's go back to what we were talking about just a minute ago.
Wait, Dr. Harrell.
Yes, yeah.
When you were building that,
Mm-hmm.
can you explain the parabolas that you put in there one more time?
Yeah, look, because they're reciprocals of each other, right? So if I had the cosine was 1, 1 over 1 would be 1. So it touches right there. You see, do you see that it touches right there? 1 over 1? Yes. If it were if the cosine were 1/2 here, and you took 1 over 1/2, it would be 2. So what it does is flip those values, and it sort of flips the graph on top of it.
Okay.
Okay. So that I got a worrisome note on my internet, guys. It said my internet is unstable. That's scary here. If you lose me, I will go back and try to sign back on again. You do the same thing. Okay. It happened to me the other day and nothing happened, but I'm a little worried. But Haley, did that answer your question?
Yes.
Okay.
Will there be another one between 3 pi and 2 pi that looks like the parabola between negative 1 and
right here.
pi over 2?
If you were to
negative pi over 2?
Yeah. If you were to extend this right here, there'd be another asymptote, and then there'd be another
one. Okay.
Does that make sense?
Yes.
Okay, good.
Sorry, I just want to make sure everyone moved on.
No, please, guys, ask me questions. That's what I don't want to just be a canned lecture on the TV or the whatever, the computer screen. So let's go back to what we were doing here. Notice that the whole question was, where is this thing right here? Where are the coefficients continuous? Well, this is continuous everywhere except those odd multiples of pi over 2. Notice that your condition is at 0. Okay, so you can't say that it's everywhere, that we have a unique solution everywhere. We have to pick whatever interval we can, as large as possible, that contains 0, 0. So going back to here, if I said, okay, are we guaranteed a unique solution? And get back to my red here. Oh. Are we guaranteed a unique solution? And on what interval? What interval would you pick there? It's got to include the 0, 0, which of course is right there. So what's the biggest interval I can pick so that all my conditions hold, guys? That includes your initial condition. That includes your 0, 0.
Negative pi over 2 to pi over 2?
Yeah, exactly. Just choose negative pi over 2 to pi over 2. So it can have a guaranteed unique solution from minus pi over 2 to pi over 2. Okay. So guys, on one of your homework problems, it's going to ask you these questions. Are you guaranteed a unique solution? If so, what interval? I know a lot of times on the homework, you kind of forgot about the second half of the question, but it's important. So you've got, right now for this theorem, you've got 2 conditions. This thing right here can't be 0, and that the coefficients have to be continuous, okay? So there's 2 reasons you're not necessarily guaranteed a unique solution, or if you're guaranteed a unique solution, it would be in this particular interval. Okay. Okay. Everybody okay with that? Can everybody see what I'm writing on the screen? Everybody okay writing on the screen? I don't think. Let's see, Saron, I'm not sure I unmuted you. Hang on. I'm having a hard time with some of the unmutes. Okay, there we go. Okay, Saron, you're live, okay? All right. So, all right, so let me move on. All right, the next thing we did was something called boundary value problems. A boundary value problem, I'm gonna take just a second order one for the same idea. A boundary value problem is, again, a linear nth order, second order in this case, DE, subject to conditions, but those conditions are not at the same point. Notice before they were all evaluated at 0, or they could be all evaluated at 1. It doesn't have to be 0, but they have to be the same. In a boundary value problem, they're different. And we can have differing things happening here. What this means is that we want to find a solution to the DE that goes through the point A, Y naught. So right there, let's see here, right there, it's got to go through that point A, Y naught, and it's got to go through the point B, Y1, so maybe right there. So so those are conditions. The conditions we had on initial value problems really had to do with things at one point. For instance, a point on the curve, the derivative at that point, the second derivative at that point, and so on. But here the point can change. And not only can the point change, you can have any combination of a point and derivatives of the other one, or derivatives of the point and derivatives of the other one. So you can have any of these things. The point here is that A and B are different in each case. Otherwise, it's an initial value problem. Okay. All right. So so let's look at a couple of examples. What happens? What's different on an initial? on a boundary value problem is this. Even when the conditions of that theorem I just gave you are satisfied, anything can happen in a boundary value problem. It can have a unique solution, no solution, several solutions. So you have to be, you don't know. So you have to figure it out. And this is the topic of a couple of the homework problems. What I did in class that day long ago, that Wednesday before we left for our extended break, was an example where I showed you what could happen in certain cases. It was example 3 on page 119, and I'm going to do one piece of it, and then you can go back and look at the other pieces and see what happens. The DE was x double prime plus 16x equals 0. Now, if this had been an initial value problem, I got constant coefficients, everything's continuous, nowhere this is going to be 0. That would be guaranteed a unique solution. That is not the case. That is not the case here. So, for example, what you could do is look at the 2-parameter solution. Now, I'm telling you, the book's telling you here's the solution. You can verify that if you want to, and you would verify it much the same way we've always been doing it. We take 2 derivatives, put them in here, and see if it equals 0. But that's a solution. Now, suppose we impose the boundary value conditions on it. And these boundary value conditions here are x of 0 equals 0 and x of pi over 2 equals 0. So what I'm going to do is take each of those conditions and plug it into the solution so I can see what the C1 and the C2 are. Okay? So the first thing I did was take this 0, 0 one, this one right here, and I plugged in 0, 0 for t, and the value of the function there was 0. So I plugged in 0 here, 0 here, 0 here. So for t, t, and the value of the function. This function is called x. Notice when you go through that, the cosine of 0 is 1, so that's 1. The sine of 0 is 0, so that means that this one drops out. That means C1 is 0. Now, it means something else too. Because this dropped out, it always is going to drop out because the sine of 0 is always 0. That means C2 can be anything I want it to be. So in other words, that condition tells me that C1 has got to be 0, so that term right there drops out. And then C2 can be anything. Now, so C2 is arbitrary. If C2 is arbitrary, how many solutions are there going to be here, guys? Anybody? How many solutions are there going to be? Yeah, but C2 can be anything I want it to be, so how many solutions?
Infinite.
Infinite. Infinite number of solutions here. So if I look at this, I'm going to just write, let's see, let me write that here. So what we get here is infinite. Because of this, that can be anything I want it to be. All right. So if I plug in the next condition, so we'll look at the next one. This is when I touch the screen with my pen, with my hand. It I'll get rid of that. It makes a mark. So here's what I'm going to do. I'm going to plug this other one in, and if I plug in pi over 2, notice that I get C1 times the cosine of 4 pi over 2, which is 2 pi. Cosine of 2 pi is 1, so that's why that's C1 times 1. Again, the sine of 2 pi is 0, so I get C2 equal 0. And again, that makes it true all the time because 0 equals C2 times 0 is 0. That means C2 can be anything. So what does that tell us about what's going on here? It tells us that C1 has to be 0, but C2 can be anything. So x of t equals C2 sine 4t. If you look back at the original equation here, this one right here, C1 had to be 0 according to this condition right here. C2, according to both conditions, could be anything I wanted it to be. So let's look and see what the solutions look like. What if C2 is 0? What would the solution be if C2 were 0 here, guys? Well, if C2 is 0, does it matter what t is? Not a bit. What would it be? What would that solution be? Anybody? Talk to me, please.
Is it 0?
It'd be 0. So I can draw a solution on here. One of those solutions is that solution right there. That would be the solution that corresponded to C2 equals 0. Okay. If I let, let's see, let me go blue here. If I let C2 be 1, it would look like a sine of 4t. Now, guys, I've already sort of played out the graph for you. What this does is speed up the period of this thing. Instead of the period being 2 pi for just sine, it thinks things happen 4 times as fast. So 4 times 2 pi is pi over 2. I don't know if you remember that or not. But what happens there is that if I looked at C2 being 1, what I know I'm going to get is a sine function starting here. and going there. So that doesn't look too good. It should go all the way down to -1, but it looks like that. If C2 were 2, it would look like that. It would go all the way down to -2. So what you got here are infinite solutions. I'll show you one more. If C2 were -1, instead of the sign going up and then down, it's going to go down and then up. So that one would look like that. So that would be C2 is -1. This one right here is C2 = 1. This one right here is C2 = 2. So I get infinite solutions is my point. It can be, I can let the amplitude is what's changing there, guys. The amplitude can be anything and it'll satisfy this. And notice all of those go through 0 and pi/2. They satisfy the conditions. X of 0 is 0 and X of pi/2 is 0. Now, you do need to read the rest of this example because when they change the conditions, different things can change. So make sure you read that example in the book, and I think that'll help you with understanding that. Now, the homework that's due on Thursday, I made a mistake. These are just the general homework problems that were due, so those are things to work for your own benefit. The ones I want to see I made a mistake here because I changed it to Thursday instead of Wednesday. I originally thought Wednesday, but I changed it to Thursday. Okay, so I'm going to say Thursday, and that'll be 4-2.
Dr. Harrell,
Yeah,
can you just scroll up for like 2 seconds so I can get one note?
absolutely. Say it again. Can I do what?
Can you scroll up to
Yeah.
the plugging in section that we
Yep.
just did?
Yep.
And this,
Yeah.
that's fine.
Yeah. Okay, right there.
Yeah, that's
Okay,
good. Just
please
like 2
stop me
seconds.
because I don't know how to pace myself real well on this. So please stop if there are things you need.
No, you're fine. That's all I
Okay.
did. Thank you.
Okay. Okay. So so the homework's due on Thursday, and I'm going to try to have all these homeworks due by 5 o'clock of whatever day. That leaves the nights for grading. That leaves the days for teaching, the nights for grading, and the wee hours for I don't know what, writing lectures. Not sure, but anyway, are we okay on that? Is everybody okay on that? Okay, so that's sort of the end of that piece. That's the review. That's section 4.1.1. Okay, so I'm going to go back. There's something I need to teach you before we go into the next section, and that is something called the determinant of a matrix. Now, I want to see if I can hear the people who have had linear algebra. Saron, I know, has had linear algebra. Who else has had linear algebra? Tell me.
I
Anybody
took
else?
it last semester.
Who took it last? Sylvia, you took it?
I
Yeah.
took it too.
Okay. Who
I did
else?
too.
Allison?
Sierra.
I have not.
Okay. All right. Let me tell you that the people that have had linear algebra are probably going to remember what a determinant is. And the people who haven't had linear algebra are not going to remember what a determinant is. And maybe, I don't know, some of you may remember why it's important. Some of you may remember why it's not. So that's why I'm going to put a lecture in here, or I'm going to talk to you about the determinant. So let me get to that one and we'll talk about the determinant. Okay, some of you may have had this in high school because there's a section in high school where you solve systems of equations using determinants. May or may not remember that, doesn't really matter. But basically what we're dealing with here, guys, is this. We're talking about matrices, and we are associating with a matrix a real number. And to just remind you a few things about matrices, we talk about matrices as how many rows and columns they've got. So a 2 by 2 is 2 rows and 2 columns. A 2 by 3 would be 2 rows and 3 columns. When we're talking about the determinant, we're always talking about a square matrix. And you can guess what I mean by square. It just means it has the same number of rows as columns. So this determinant thing is only defined for square matrices. So here's the first little rule I want to show you about determinants, and this one will go a long ways. We are only going to deal with in this class how to take 2 by 2 determinants and 3 by 3 determinants, but matrices, determinants of those kinds of matrices. Determinants get really hard to compute when you get bigger matrices. But the first one is easy. And by the way, we denote it by these 2 lines around it like that. And some of my handouts, guys, I can't figure out quite how to get the 2 vertical lines around it. So if I say find the determinant and I just list the matrix, it should have those 2 lines about it. But the determinant of a 2 by 2 matrix, and we'll just say that it has components A, B, C, and D, is always AD minus BC. And the way I remember that is that you go across this way, you go AD, and then you subtract going back that way. So it's AD that way minus BC. So go down diagonally and then subtract. All right, so if we look at this matrix right here, the determinant's going to be 2 times 4, so right here, minus 3 times 1, and that's 8 minus 3 is 5. So what you've done is associate a number with a determinant. It's a function. It's a function that has a domain with matrices in it and has real numbers in its range. All right, look at this one down here. Whoops, daggone it. Go to my eraser. I keep marking on things. If I look at this next one, 2 times 6. If you look at this, look at the thing, it's like the determinant's going to be 2 times 6 minus 3 times 4. And that's going to be 0. So guys, if I gave you this one, that's 5. Tell me what that one's going to be. Do it, calculate it real quickly and tell me what that's going to be. Anybody? Go down this way, cross that way, that way. So what's it going to be? Anybody? Isabella, what's it going to be?
Negative 13.
Yep, it's negative 13. Okay, it's negative 13. Right, is anybody that doesn't know how I got that? All right, now, here's the fun part. I need you to remember something from Algebra 1, or maybe 2. If I had a system of equations that looked like this, and my variables were C1 and C2. By the way, this thing got cut off. This thing over here on the right should be 0, 0. It got cut off a little bit when I'd scanned it in. That's equal to 0, 0. If you look at this system of equations and I ask you to solve for C1 and C2, think about it as X and Y, however you want to. But if I ask you how to solve for that, you guys might use something like elimination. If I were going to eliminate a variable from this, and let's just decide that we want to eliminate C1, what would I multiply this equation through by, guys, to eliminate that C1 there? Sylvia, tell me what I would multiply by. What would you multiply by to eliminate that C1 there? Multiply this equation by something. So what would I multiply that by? Negative. So when I added the 2 together, these would drop out. Those 2 right there would drop out. Now, what would give me minus 4?
Negative 2.
Yep, negative 2. That's good, okay? So if I multiply by negative 2 here, that's going to drop out. But in the process, what happens with this? What happens when I multiply this one by minus 2?
Negative 6.
It's also negative 2. It's negative 6, right? That one drops out. So what you get is 0 equals 0 there. Well, let's think about from algebra what that means. what it really means is that those are the same equation, really, aren't they? I mean, they say the same thing, because when you multiply this by 2, you get the same thing as you had right there. So it's redundant. So the only one that really matters, so they're really the same equation. So you only need one of them. And the question would be, well, how many solutions are there to that? Well, you know what? If we were thinking about this as 2x plus 3y equals 0, that's just a line. How many points are there on a line? How many points are there on a line? How many things are going to satisfy that thing right there? How many points on a line? Well, infinite number, right? So there are actually going to be infinite solutions to that. If you remember back from algebra, you have 3 things that can happen. You can have no solution, one solution, and infinite solutions. And if things drop out and you've only got one thing left, that's infinite solutions. And I'll show you what that means. If I go back, hang on one second. If I go back to this expression right here, this is sort of, if some of you have had vectors, and probably most of you have had vectors, but if you say C1 times 2, 4, and C2 times 3, 6, that's a way to write this. 2C1 plus 3C2, and there should be a 0 over there on the right. And this one will be 4C1 plus 6C2 equals 0. There's a 0 over there on the right. What it says is you could take as many different C1s and C2s as you wanted and make this a true statement. So for example, if I go down to here, let's see. If I go down right here, whoops, let's go back this way. Here. If I go down right here and I let C1 be 1, and this is the thing that's true. If I let C1 be 1, then C2 would be minus 3/2. If I let C1 be 1, or any time, C1 is going to be minus 3/2. So let C1 be 1, C2 is going to be minus 3/2. And if you put those here, you'll get a true statement. I can let C2 be anything I want because there are infinite number of points on this line. If I let C1 be 3, or C2 be 2, let's say. If I let C2 be 2, let C2 be 2, then that says C1 will be minus 3. So I could write, let's see, minus 3 times 2, 4, plus 1 times, oh no, not 1, but 2, times 3, 6. 3, 6, I didn't mean to put that line there. Let's see, 3, 6. Okay, I should get 0 there. Okay, so you've got infinite solutions, is what I'm trying to tell you. Okay, now I'm going to ask you this: what was the determinant? Let me see. And I wrote it down a little more detail down right here. But what the determinant of the one that I was just looking at, if you look at 2, 3, 4, 6, and think about what the determinant would be. 2 times 6 is 12, minus 3 times 4 is another 12. 12 minus 12 would be 0. All right, let me show you one other thing here. Suppose we looked at the other one we had, another one we had. So if you look at this one as the matrix having in it 2, 1, 3, 4, what's the determinant of that one, guys? What's the determinant of that matrix right there? Cross it, it's 8 minus 3 will be 5. Now notice, if I make a system of equations out of that, right here, there would be 2, 1, and 3, 4, and I solve the system, And here's how I solved it, guys. I multiplied the bottom one by -2, right here. That dropped out, but this one now says -5C2 equals 0. So that means C2 has got to be 0. And if C2 is 0, go back up to C2 is 0. Go back up to either one of the other equations. If C2 is 0, that's 0. And 2C1 will be 0. That means C1 has to be 0. So I'm forced here to say the only solution is 0, 0. So the only solution here is the point 0, 0. Now, the thing I want you to notice here was that the determinant was non-zero. Okay, some of you from linear algebra may be remembering this, but I'll bring it all together for everybody else. Here's my conclusion. So if we've got this kind of system of equations where you've got a system so that the matrix times whatever your variables are is 0. In other words, you've got a system of equations all equal to 0, like I had. If AD minus BC equals 0, there are infinite solutions. All right, there are infinite solutions there. If AD minus 0, if ABCD, if the determinant is not 0, then there's only one solution. 0, 0 is the only solution. Okay, so if the determinant's non-zero, 0, 0 is the only solution to this homogeneous thing. If it's 0, there are no solutions. Yeah, question.
Can you zoom or slide back up just a second?
Yep.
I have a question about.
Right there.
So I remember, yeah, during before our first test, when we were sort of kind of building these things, when we were doing 2-parameter families, and we were trying to.
Yeah.
I remember just adding just across, like if we had, for example, in the part where it says that is the system 2C plus 3C equals 0.
Yeah.
I would add 3C1 plus 7C2 equals 0. Is that what we were doing before?
We might have been solving it a little.
This is when I was trying to solve for. So forget that. I guess right now what I'm trying to do is try to cancel out one of those constants by adding and making it equal 0.
Exactly. And guys, there's another way to solve this. Remember substitution? With substitution, if you look at this, you could have solved, if you look at that thing right there, you could have solved for C1 in this one. So C1 equal minus 4C2 and plugged it into that one, and then you could have solved it that way. With only 2 equations, it's easy. 2 equations and 2 variables. Elimination is usually the easiest thing to use. So does that help, Haley? I'm not sure.
Yes.
Okay.
Right. So what was the point in the beginning of saying that whole matrix was equal to 5?
The determinant was 5. Here's the whole point, guys. If the determinant is not 0, okay, if the determinant is not 0, then notice what we got for the solution for this one right here. See that determinant right there, 2 times, whoops, be careful, 8. See this 8 minus 3 here? See that? Okay, that was 5. The determinant was 5. If the determinant of those things is not 0, then the only solution you're going to have is 0, 0. See how I got the solution 0, 0 here? I got, it had to be 0, 0.
So right where you just checked, we made C1 equal to 0, correct?
No, I didn't make it equal to 0. What I did was I multiplied this equation right here by -2. I added them together, and those dropped out. And then all I had was minus 5C2 equals 0. Well, if that's the case, what does C2 have to be?
0.
It has to be 0. I just solved the system, okay? And if C2 had to be 0, you could plug in C2 right here and you'll find out that C1 also, 2C1 has to be 0. That means C1 has to be 0. You just solving 2 equations in 2 variables. But the big point for me is this.
Oh, you went back and plugged it in. That's what you did. To
Yes,
find
I went back and
C1,
plugged
right?
it in.
Okay.
Yes. Here's the big point for me, guys. Suppose I gave you this system right here. 2x plus 3y equals 0. And minus x plus 4y equals 0. That was bad. But anyway. Tell me, and the coefficient on this is -1. So the associated matrix is 2, 3, -1, and 4. Tell me what the determinant of that is. Tell me what the determinant of that matrix is right there.
9.
8 minus not 9, I don't think, but
11.
It's 8 minus a -3 will be 11. Okay, here's the point. If you've got a system of equations like that, or you're looking at what we say at sort of a linear combination of these columns right here, if you get something that's not 0, the only solution to this is going to be 0, 0. I know that. So see, that's what I had said right down here. If the determinant's not 0, then 0, 0 is the only solution. And if you guys solve that one right there, you'll find out that the only solution is 0, 0. This is a big, big thing in linear algebra. Those of you who are in linear algebra, remember you kept adding lots of things onto what I call the big theorem. And one of them had to do with solving systems AACC. We'll come back. I'll show you how it links up with everything else we're doing, okay? I'm just right now just worried about how to find the determinant. And that if the determinant's non-zero, it means something about the solution, okay? If the determinant's 0, there are infinite solutions. If the determinant's non-zero, there's only one solution. What do we call that, guys? I mean, we almost always call it the same thing. If 0, 0 is the only solution, do you remember what we call it?
Trivial solution?
Yeah, it's a trivial solution. Okay. Which doesn't mean it's not important. It just means it's 0. Okay. All right, let's go a little further. I don't want to. Okay, let's go just a little further. This will be the last thing we do. Okay. What if I want to find a 3 by 3 determinant? So this is a 3 by 3 matrix. It's got 3 rows and 3 columns. And I want to point out to you, and this is just a little trick, and you can keep looking at it. It comes pretty easily. If you look at how we denote things in a matrix, I use double subscripting to denote things in a matrix. A11 means it's the entry in the first row, first column. So that would be 2. A12 is first row, second column. A13 is first row, third column. So A32 would be third row, second column. Now, associated with a general matrix is what I call a sign matrix, S-I-G-N, this thing right here. Look at that entry right there. Add up the subscripts. What kind of number do you get? Even or odd? If you add up the subscripts, what do you get? You get a 2, don't you? If you add up the subscripts on that one, you get a 4, which is also even. Any things I should circle in this row right here? Which one's even there if I add up the subscripts? Which one there? Anybody?
Middle one.
The middle one, exactly. If I add up the subscripts, those are all even. In the third row, it's this one and this one. Notice on this sign chart down here, where I had the even ones, I have plus, 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 plus. All the other ones, if you look at those subscripts, they add up to odd numbers. So where those are, I'm going to put a negative sign. All right, so if I do those are the ones that get the negative sign.
it should pop up and we can take a look at it for you.
What's that?
You're welcome. Bye-bye.
I can't hear you again. What? Who's talking? I can't really hear. I can't hear. If the
It sound like background noise.
Oh, okay. All right. Thank you. Okay. So, so again, guys, if it's here and here, 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 and here, it's going to be associated with a positive. And I'll tell you why that matters. Here's how I'm going to find the determinant. I'm going to pick the first row. And theoretically, I can pick any row or any column. But to make this simple for everybody, I'm going to pick the first row. I'm going to take this entry right here. Let's see. I'm going to take this entry right here, and it goes right there. And because it's in a positive spot, I'm going to leave it positive. Okay? And then I'm going to look at the determinant of the submatrix I get when I delete the row and column that number's in. So if I delete the row and column that 2's in, I will get 0, 4, 1, 2. So let's just write that down. Okay? Now,
You delete what?
delete, see where that 2 is, and delete the row and the column that it's in.
Oh, okay, I got you.
Everybody, and so see, guys, what's left is 0, 4, 1, 2. Everybody see that? 0, 4, 1, 2. Okay, now, that's the first thing I'm going to do. The next thing I'm going to do is erase what I just did. Oh, well, yeah, it won't mess up my, that's cool. It won't mess up my PDF, it'll take that off. Okay, here's the next thing I'm going to do. I'm going to take the next entry, which is 1, but because it's in a negative position, it's in this odd position, I'm going to make it negative. So that's how that got negative.
Wait, if negative 1 is already negative, would it become positive?
It becomes, yes, it will become positive. You see, I'll just take the opposite sign of the blue one.
Gotcha.
Okay, I take the opposite signs of blue. So there's a -1. All right, I'm gonna, that's what I did there. And then I'm gonna delete the row and column that it's in. I'm gonna delete the row and column that it's in. And look what's left, guys. -1, 4, 3, 2. So I'll write that down there and put a determinant sign around it. Notice what I'm doing is I'm changing these to 2 by 2 determinants, which are easy. Okay, is everybody with me on that? So I took the 2, I deleted the row in the column, the 2's positive because it's in a positive spot. And I took the subdeterminant, we call it. And then there's 1, it's negative, I make it negative, or I change its sign. I just change its sign there. I put a -1 there and then delete that row and column, and what I'm left with is that. Last thing, let me get that erased. The next thing I'm gonna do is take this entry right here, that 3. I'm gonna put it down here, and I'm gonna leave it positive because it was in a positive spot. See the spot it was in? It was in a positive spot. Then I'm gonna delete the row and column that it's in. And what you'll see is left is -1, 0, 3, 1. Okay. So, all right. So let's finish it out. I'll do another one. I'll set up another one. Okay, I'm gonna finish it out. Notice here that this one right here would be 2 times, and the determinant, the subdeterminant, remember how I found a determinant of a 2 by 2 matrix? I went across, and then I subtracted. Multiplied these, and then subtracted these multiplied. So I'd get 0 minus 4 times 1. And that's how I got that. All right. This one right here, I probably should have put a -1 to indicate to you that that still's there. This would be -2. Come across this way. -12. minus 2 minus 12. I'll compute it in a minute. The next one is a 3. That came down here. Go across this way is minus 1. 0 times 3 is 0, so it's minus 1 minus 0. And when I compute that, I get 3. I get 3. All right. I'm going to move it up to another example, but does anybody have any questions about this example? I'm going to just do another one. I'm sure those of you who have linear algebra remember it, or maybe try to forget it. I don't know. Okay, so let's move up to another one. I'm going to try this one. Okay, I want you to take a few minutes just to write out what you think it is, and then we'll compute the thing. Okay, take a few minutes to try to find the determinant. Now I'm going to use the first row, 1, 2, 3, and I'm going to give you, I don't know, I'm going to give you a couple minutes to do that. All right, guys, let's see if you're on the right track. You have to be really careful with this. If you hit and you can do this with any row or any column you want, but I usually just pick the first one. It's just easiest for us to do. What I did is take 1 and put it right there. And then the subdeterminant there, if I delete this and this, is 1, 0, 3, 2. So I'm going to do it in little pieces here. And then I get to erase. Okay, that's the first thing. The next thing I did was take the 2. I made it negative because it's in that odd position. It's negative position. When I delete the row and column that it's in, I'm left with 4, 0, minus 1, and 2. Okay. And I'll erase that. So if I now pick this element, whoops, if I pick that element, it's in a positive position, so it's 3. If I delete that row and column, I get 4, 1, minus 1, and 3. Okay, let's finish it out. 1, This one right here, guys, will be 2 minus 0. So that's 2. This one right here will be 8 minus 0, which will be 8. This one right here will be 12 minus a minus 1, which will be 13. Be careful with your signs in here because you're subtracting, but if you get a minus, you're going to obviously change the sign. 12 minus a minus 1 will be 13. All right, let me see what I got here, guys. I got 14 minus 14 plus what, 39 minus 14 plus 39, and I get what? What is that equal to? 25? Who got 25? Am I the only one that got 25? Anybody get
I got
25?
25.
Yeah.
25? Isabella, you get 25? Sylvia, you get 25?
Yeah.
Okay. Saron, you okay?
Yeah,
25?
I got 25.
All right, Allison, I've got a whole bunch of other people on here. Haley, Allison, Brittany.
Yeah, I
You
got
hear?
25.
You got 25? Okay. So guys, here's what I want you to do tonight. I want you to just look at that assignment sheet. Let's look back at it one more time.
Could you email us that assignment sheet so we can print it out?
It's on Moodle. Thank you for
Sorry,
reminding me.
okay.
It's on Moodle, guys. I'm going to try to put all of these typed out things on Moodle, okay? And remember, the other thing that's going to be on Moodle is the link. I'm hoping this will work. Who knew you could only upload a 15-minute video to YouTube? Not that I ever tried it. It didn't really matter. So I had to apply for longer videos. I'm sure these will be of enormous interest to most of the world. I got a 12-hour limit. I'm like, okay, that should be enough. This will all be up where you need it. If I look at this though, guys, here's what I got on this for tonight. I've put 2 determinants on there. I'll come back and give you the answers to those on Wednesday. That's just homework. These are the sort of practice problems on the initial value problems and the boundary value problems. We have not gotten to this yet. The only thing that's due is due Thursday, and that is these are a few IVP and BVP problems. You might want to look at those as you're doing those. And I covered everything I think you'll hit in this. All right.
We can do those as
Yes.
of right now, correct?
As of right now, you can do these because they were just am I guaranteed a solution? On what interval am I guaranteed a solution? Those kind of things. Okay.
And
So
I know
pretty
you
fun.
mentioned this, but does that work with both editions of the book?
Say that again.
Does that homework work with both editions of the book?
Okay, here's the other thing I've done. Thank you, Haley. You reminded me of everything I was supposed to tell you. I have also, because of the book issue we've got, I have also put on Moodle a scan. It's a little bit fuzzy, at least on one page, a scan of the problems I'm expecting you to do, okay? So if you click on that on Moodle, it'll say, number 1 assignment, whatever. You'll see that's the page 128 or whatever it is, 127 and 128. I thought about that at the last minute, and I was like, man, having a different book was a pain in the butt before all this happened. Now it's really bad. Made me want to go over to the bookstore and never mind, break in. Anyway, so I have put that up there so everybody's doing the same problems, okay? Anything else? Any questions, guys?
I have one. It's kind of unrelated, so this doesn't pertain to anybody else. But how did you update the Zoom so you could do more than a 40-minute session?
It turns out that you can go in. I thought that they were doing that automatically for academic addresses, guys, because of the situation that we're in.
Mm-hmm.
So I think I hope nobody's gotten bumped off. Nobody got bumped off?
Mm-hmm.
Okay.
No, I had other professors, and they're doing like a really roundabout way of doing this. So I was going to email them and tell them they can get unlimited Zoom time.
I think that Zoom has, in the Corona crisis, has said they know people are going online and to do their classes, and they've hooked you up so it's unlimited. Okay.
Thank you.
At least that's been I hadn't gotten anybody bumped off yet. Let's just put it like that. Okay.
Okay.
And I've been going an hour and we got 15 minutes. And I'll answer any questions like I usually do the beginning of class. I'll give you the answers to those determinants. If you got any questions about the homework that's due, or you had questions about the homework that's like that homework, you can ask me. And we'll go from there and make the best of this. It's a weird, you guys are living through really interesting times. That's all I can say. And me too, actually. I'm not dead yet. So we'll do what we can do. All right. We'll take care of business. Okay.
Thank you.
All right. I'm good. I'll post the thing up to Moodle. I mean, up the link to the recording up to Moodle as soon as I can. And I will see you on Wednesday. All right. And I'm going to see if I can figure out how to end the meeting. Oh, here it is. The meeting is officially ended. See you guys later. Bye.
Thanks.
Bye.
Thank you.